Welcome to my class. Today I want to teach you how to determine if a given set is a vector space, and that's what I will start with. Then later on I'll teach you how to determine if a given subset is a subspace. So I begin by first of all defining what a vector space is, and I said we can also call it a linear space. And a vector space is just an empty set together with the two algebraic operations, the operation of addition and that one of multiplication by scalars, that fulfills the following properties. So it must fulfill these 10 properties. And the first property is that of closure. Now, what you notice is that the first 5 properties are the properties of addition, vector addition. So this one is that one of closure, that if you pick any 2 elements in the set, the sum of those 2 elements must be a member of that set B. And then the second one is commutativity. Commutativity, that it must be commutative. That you pick, if you are to pick any 2 elements x and y from V, then the sum of x and y must be the same as y plus x. And then the third one is associativity, that's additive associativity. And then we have this, that it must have an identity element. So the identity element here is 0. That x plus 0 gives you x, or 0 plus x gives you x. So 0 is the identity element, additive identity element. And then every element in this set must have an inverse, an additive inverse. So x plus its inverse gives you the identity element. Then these other properties are the ones for multiplication by scalars. And this is the closure. That if you are to pick a vector x and a scalar a, the product of this scalar and the vector must be in V. So this is the closure property. And then one here is the identity, multiplicative identity element, that there must be a multiplicative identity element, such that if you are to pick an element x from the vector space and multiply it by this identity, you get x. Or if I was to take 1 times x, I would still get x. And then we have this distributivity property. This is the scalar distributivity. So if a is the scalar multiplied into x plus, no, y plus z, where y and z are elements of the vector space, then when you distribute this scalar inside, you get ay plus az. So this is the scalar distributivity. Scalar distributivity. Scalar distributivity. Now we have the vector distributivity here. This is a vector, and we have the scalar a plus b. So when you distribute this scalar, this vector inside, you'll get az plus bz. So this is the vector distributivity. And then finally we have the associativity. Associativity as a scalar associativity. Now I have this scalar a, and there's this bracket bx, where b is another scalar and the x is a vector. So this one gives you, just change the position of the bracket, and I have ab, then x. Now, these are the properties of a vector space, that a vector space must satisfy these properties. So as I've already said, a vector space will just be an empty set. That means a set with the elements, together with the operations of vector addition and multiplication of vectors by scalars, satisfying these 10 properties. Now, there's something I've said here. I've said that the items 1 and 6 imply that the vector space is closed under addition and scalar multiplication of vectors. Now, this I say that this is the closure property. Closure under addition. Under addition. This is the closure property. And under multiplication, this is the closure property. Under multiplication. And I've already said what others mean. This is commutativity, this is associativity and addition. This is the existence of the identity element, that there must be an identity element. And this one is the existence of the inverse, that every element must have an inverse. Now, so if you're asked to tell if a set is a vector space, then what that means is that you must go through these properties and see that they are all satisfied. If any of them is not satisfied, then that set is not a vector space. Now, so what I'll be showing you today is not actually to go through all the 10 properties to tell if a set is a vector space, but I'll want to just be using this. I'll be using this. It's enough just to use this first property and the sixth property to tell if a set is a vector space. If these two are satisfied, then the rest will automatically be satisfied. If any of this is not satisfied, if any of these two is not fulfilled, then that set does not qualify to be called a vector space, and therefore it will not be a vector space. But let me just show you a few examples. And the examples that I want to show you now how to determine if a set is a vector space, determining if sets are vector spaces. And I've already stated this. I'm just repeating, and I've said that to check if a set is a vector space, it is enough to check if it contains the zero vector, that is, if it's non-empty. So what this means is that V would be a vector space if it is not empty. And how do we say that it's not empty? We say that it's not empty if it has elements. And the easiest element that we're looking for is if it contains zero. If V contains zero, then you see, for it to be a vector space, it must contain zero. So that is the first thing we'll be checking. Then the second thing we'll be checking is the closure property and addition. That if I was to pick any two elements, X and Y from V, then the sum of these two must be V. So I'll also be checking that to see that it is fulfilled. Then finally, I will check closure under multiplication by scalars. That if I were to pick a scalar A from the real numbers and pick a vector X from V, then the product of A and X must be V. So I've been looking for these three conditions, and these three conditions, they must all be satisfied for a set to be a vector space. Now, if one of them is not satisfied, then it's not a vector space. You don't need to show. If once you discover that one is not satisfied, you don't need to proceed and look and prove that others are not satisfied. You just show one, just show one, and that is enough to disqualify a set from being a vector. Let's look at the example first. The example says show that this vector containing AB in R2, where A is non-negative and B is non-negative, is not a vector space. So that this is not a. So the other way of writing this is this. Let me just show you how it's also written. You can even write it like this. There's no problem. If you find somebody has written it this way, there's no problem. It's the same thing in R2. It is supposed to be R2. It is supposed to be double R. And such that A is greater than or equal to 0 and B is greater than or equal to 0. So if this is the other way of writing it, so you don't get confused when you find it written this way instead of this format. This is just a vector. You can write it in column form or in row form. Now, so how do we answer this question? The question is show that is not a vector space. So in other words, of the three conditions that we've talked of, one, that it must contain a 0. We must show that it contains a 0. We must show that if you pick two elements x and y, then their product should be in B. We must show that if you to pick a scalar A and a vector x, their product must be in B. So we're asking, the question is, we must show these three to show that it's a vector space. But if it's not a vector space, in the way the question is saying that shows that it's not a vector space, just think of which of these properties that is not satisfied and just give us that. You don't need to give us all these three properties. Just think of one that you believe that it will not be satisfied by this set. So that is the one you give us. Now let's see. This set of course it has the 0 vector. Because they have said here that A should be greater than or equal to 0. So A can be 0. A can be 0. And B should be greater than or equal to 0. So B can also be 0. That means this B contains 0 vector. So that the first property is satisfied. So that we have no problem with that. So we are looking for one that is not satisfied. Let's look at the second property here. I want to pick two elements. Let me say two sets, no, two vectors. Let me say U from V, and I want to pick 1, 2. And also pick V, and I want to pick 3, 2. If I was to get the sum, U plus V, this would be 4, 4. When you add these two vectors, it will be 4, 4. And you notice that our A here is greater than 0, and our B here is greater than 0. So this one is in B. This one is in B. So this property is also satisfied. That if I were to choose any two vectors from V, their sum will be B. So the question is, which of these three properties is not satisfied? Let me check the last property. We are not limited on how to choose the scalar. I want to choose a negative scalar. I want to choose a negative scalar, and let me I chose negative 3 as my scalar. And I want to choose a vector from V, and I chose 2, 1. I want to see if the product will still be V. So the product of negative 3 and this vector is negative 6, negative 3. Negative 6, negative 3. Now my A is negative 6. My A is negative 6, and my B is now negative 3. And I can see that negative 6 is not greater than 0. Is not greater than 0. And this one is also not greater than or 0. So that means the product of this scalar and this vector is not in V. In other words, V is not a vector space. V is not a vector space. So I've gone through all the properties, all the three properties, until I was able to find one that is not satisfied. And the one that is not satisfied is the third. So if you can just think very fast and tell which one will not be satisfied, it's just enough to give us that one instead of going through all the three. Like, look at my answer the way it is. My answer, I noticed that the third property will not be satisfied. So I just went straight to the third property. So I didn't need to go through to check whether it has the zero vector, whether it has the additive closure property being satisfied. So I just knew that for this type of set, I knew that the closure property for scalar multiplication will not be satisfied. And that is what I went for. So you just need to give one, and there's no problem. And let's look at another example. Now, so the other example is this. This is the other example, and it says, is this vector, now is this set here a vector space? Is set W a vector space? And I have already told you that this one can also be written this way. So I just want you to know how to write it. This one is written in column in a row form. You can even write it in column form like this. There's no problem, and it means the same thing. It means the same thing, such that the product of AB is greater than or equal to 0. Can even write it that way. Can even write it. There's no problem. Now, so the question is this set here a vector space? So that means you go through the properties and see whether it will satisfy. And if you believe that it not be satisfied, then you say it's not a vector space. Not a vector space. Like, for instance, I looked at this. Let me see whether it has the zero vector. Whether it has the zero vector. Now, we've been told, the condition that we've been told is that if I were to choose A and choose B, then the product of this A and B must be greater than or equal to 0. That is the only condition you are given, and it's very important to observe it. That is, it means if A was to be 0 and B was to be 0, then AB would be 0. And so that means this set has the 0 vector. It has the 0 vector. So you can see that this condition would be satisfied because this would be greater than or equal to 0. So the 0 vector is in W. The 0 vector is in W. That means the first condition is satisfied. So I have no problem with that. I have no problem with that. I want to see if they'll all be satisfied. Now let me choose another vector. If I was to choose x as 2, 1 and y as 0, -3, and I want to check the closure, additive closure. If that closure property for addition of vectors would be satisfied, I just need to add these two vectors. X plus y would be 2, 1 plus 0, -3. And what this gives me is 0, gives me 2, -2. So that my A is 2 and my B is -2. Now this is what I get as the sum of these two vectors. Does this sum belong to W? So I check using this condition here. I check if this sum is in W. I know that from the sum gives me A as this and B as -2. So the sum, the product of A and B is -4. But -4 is not greater than or equal to 0. It's not greater than or equal to 0. So that means this sum is not in W, and that's what I say. This sum is not in W. So once I find one condition that is not satisfied, I conclude that W is not a vector space. W is not a vector space because I've seen that the closure property and addition is not. You don't need to proceed to find out whether the closure property under multiplication would be fulfilled. You don't need to go there. But let's just, for the sake of understanding, let's just go there. So I have this 2, 1, and I may want now to choose a vector. I may want to choose a negative scalar. No, negative scalar. Let me choose a scalar which is -2. And let me get the product of beta x and see whether it will be contained in W. So that means -2 multiplied by 2, 1. And this is -4, -2. That's -4, -2. So my A is -4. And my B is -2. What about the product? The product of AB would be 8, which is greater than or equal to 0. So that means this third condition would be satisfied. But we needed just one to show that it's not a vector space. We already shown that it's a vector space, not a vector space. That was enough. So supposing that the second property would have accepted, would have proceeded to show the third property and see whether if the third property will be satisfied and the second property will be satisfied and the first one will be satisfied, then we will then declare it by vector space. But this one is not a vector space. And we've already seen that. Now, so let's look at the next example. It's not even an example. What you're looking at now is, the next example is the next example. Now, this is the question. The question says, is this set containing A and A, where the elements are the same, where A is a real number, a vector space? It's not a vector space. So what are some of the elements here? What are some of the elements here? So some of the vectors in W are like 1, 1. These are vectors in W, 2, 2. So the elements must be the same. 4, 4 is another example of a vector in this set, and 5, 5. So long as the elements we have A there, and so on. So those are the type of these are the type of the vectors you find in this. So the question is this set a vector space? So you just need to go through the properties and see if they're satisfied. Of course, we told that A is a real number, so that means A could be 0. A could be 0. So if A is 0, then we would have 0, 0. So that means 0, 0 is in W. So the first property that we are looking for is satisfied, that it has the 0 vector. Has the 0 vector. Now let's check the closure property and addition. Closure property and addition. And what I know is that if I was to take an element like 1, 1, that is X, and take Y as another element 2, 2, If I was to add these elements, I would get, if I was to add x and y, I can see that I can get 3, 3. Just going through, I just want to understand if it will form a vector space or not. Because if it forms a vector space, then I'll show the general proof, not, I don't use examples. If it's a vector space, you don't use examples. But if it's not a vector space, you do that by using examples, the way we did earlier. Let me just show you if I proceed. That this example here, I discovered it will not be a vector space, and therefore I came up with the specific examples, chose a vector, and then chose another vector again, and added and found something that was not in W. So when you discover that it will not be a vector space, then you choose examples, specific examples, to show that they will not be satisfied, that it will not, that the properties, using those specific examples, show that the properties that we're looking for, the 3 properties, one of them will not be satisfied. Look at the example above. When I discovered that this thing will not be this set will not be a vector space, I let x be as a 2, 1, and then I choose a scalar, and then get the product. So you use a specific example when you discover that it will not be a vector space. Let me show you this one again. The other, those were the only examples we looked at. And what I'm emphasizing is that when you discover that it will not be a vector space, choose on specific examples. But when you notice that it will be a vector space, then you not choose specific examples, but you prove that it's a vector space using arbitrary elements. And that is why you're seeing that I said that because we are taking A is a real number, of course, we'll have 0, A can be 0 and 0. And so the 0 vector is in W. Then I already have at the back of my mind that this should be a vector space. So I let N and M be vectors in W, so that I can let this N be the vector X, and M be the vector PP, where this X and PP, X and P are real numbers, where X and P are real numbers. And then what will be the product, or now what will be the sum of N plus M? It's this plus that. Remember, X was a real number, P was a real number, so the sum will be a real number. X was a real number, P was a real number, so again the sum will be a real number. That means this will be a vector of real numbers, so it will be in W. I had chosen 1, 1 earlier, but I've said that you don't need to use specific examples. Once you discover that it is a vector space, you don't need to use specific examples like 1, 1. Use the arbitrary vector. So, for example, I'm just showing you this. So these are real numbers. Okay, I hope you understood what I've just said there. That if you discover it by vector space, just use the arbitrary vectors and not specific vectors. Now, again, we want to show that closure under scalar multiplication will be in W. So I choose a vector N and the scalar beta and get the product of beta N, which will be bx, beta x, beta x. Remember that N was, X was a real number. So X times any number here, any scalar, will be a real number. and x times any scalar again will be a real number. So that means this is a vector. This new vector is a vector of real numbers, and therefore it will be in W. Because this is a condition. The condition is that the elements here, A and A, they must be real numbers. So you know this will be a real number, and this will be a real number. Because our A there will be beta x, and another A there will be beta x. And since x was a real number, multiplying it by a scalar will the result be a real number. So and therefore it will be in W. So that means that the three conditions have been fulfilled, and therefore it is a vector space. So what you notice is that for you to show that it's a vector space, you must show that the three conditions are all fulfilled. But for you to show that it's not a vector space, then you only need to show us one condition that is not fulfilled. And then you conclude. And the other thing that you must have noticed from this example is that for you to show that something is a set is not a vector space, you need to use specific examples and show that using those specific examples, a certain condition is not satisfied. But for you to show that a set is a vector space, you are not using specific examples, but you are using arbitrary vectors. Okay, so let's look at subspace. So I begin by definition of a subspace, and I say that a subspace of B, where B is a vector space. So a subspace of B is a subset S of B. Must be a subset of B, such that for all x and y in S, the following conditions are satisfied. The first condition is that this S must contain the zero vector, and that if I was to pick any two vectors from the subset S, let me say I pick the vectors x and y, their sum must be in S. That means S must be closed under addition. And again, if I was to pick a scalar and pick a vector x in S, the product of R and X must be in S. In other words, S must be closed under multiplication by scalars. This is the closure property. S must be closed. Now, so a vector subspace is just a vector space. So that means, in fact, you may want to do it by showing that it fulfills all the 10 axioms we had when you were beginning. The 10 axioms fulfilled by a vector space must be fulfilled by a subspace. So a subspace is just a vector space, and that means it must fulfill all the 10 axioms of a vector space. But just as we did for the vector space, instead of going through the 10 conditions and seeing that they are all fulfilled one after the other, we just single out these three properties and test them. If they are all fulfilled, then the subset S becomes a subset, a subspace. It becomes a subspace of B. If any of these conditions is not satisfied, then this subset S fails to be a subspace. So that's what we'll be doing. So let's look at examples. Okay, so we look at examples. No, just before that, I've said determining if subsets are subspaces. And In fact, I'm just repeating what I've already said. This one is not supposed to be there. This one is not supposed to be there. So it's supposed to read to show whether a subset S of R2, R3, or Rn is a subspace. The following steps will be necessary. The following steps will be necessary. So I've erased this one. The first step is if S is a subspace, if it's a subspace, then the way we did for the vector space, you need a general proof. You need a general proof to give a general proof where you're not using a specific example. You remember that. So you need to show a general proof by showing that it contains the zero vector, is closed under addition, and is also closed under scalar multiplication. So that is what you show. So you just show a general proof if it is a subspace. And if it's not a subspace, then you need to demonstrate this by taking a specific example, which we call a counter example. And then show that this subset will not be closed under addition or is not closed under scalar multiplication or does not contain the zero vector. So if you suspect it's not a subspace, then you need to choose some specific examples and show that either it does not contain the zero vector or it does not fulfill the scalar multiplication of vectors, or it does not fulfill the closure property under addition. And so that is clear because we've done that before in our previous chapter. Now I've said that note that if the set of vectors in the subset S is to span, is the span of some of the vectors, and then S is closed at addition and the scalar multiplication. And so S will be a subspace. And we'll show an example of an example capturing this point. So when that time comes for that example, I'll make this point clearer to you. Let's look at example. Now, this is the first example. You see, the first example is here. I moved so fast. The first example is here. Show that the subset S consisting of all vectors of this form is not a subspace of R. In fact, this is how you can also write it. That show that S, which is a set consisting of the vectors under this such that X is greater than or equal to. I want you to know how to write it different so that when you get it written in a different way, you don't see it as something different that you've never seen it before. This is the other way it can be written. So if somebody writes it this way, somebody writes it this way or this way, it's the same thing. It's the same thing. Or even somebody can add here, can even write it this way. Let me just erase a bit of it and then include something. Somebody can even now write it again this way. If I erase this, and then add here in R2 such that X is greater than or equal to 0, Y is greater than or equal to. So it means the same thing, and you need to know the various ways you can write a set. You must have learned that before, that you can write as text either by listing the elements or by this. Now, it's okay the way it is. What is important here is the condition given to us is that x must be greater than or equal to 0 and y must be greater than or equal to 0. That is the condition given to us here. And the question is show that this is not a subspace. It's not. That means we must use specific examples for that. We come up with a specific example and then we think of that one condition of those three that is not satisfied. Now let me just check. Since it's not, let me check whether it has the zero vector first of all. So if the zero vector is there, and then I proceed the other condition, and see whether it will be satisfied. The other property. Now, x must be greater than or equal to 0. So that means x could be 0, and y could also be 0. That means then S would contain the zero vector. S would contain the zero vector. So this one will be satisfied. So we don't need this. Because what we need is to show that it's not a vector space, subspace. So we don't need this because it's satisfied. Now let me look at which one. Let me look at which one will not be satisfied. What are the sum of the elements in this set? Some of the elements in this set we can have an element like 1, 1. So long as the element here and the element here is greater than 0. The x is greater than 0 or equal to 0, and y is also greater than 0 equal to 0. I can also pick another element, the other vector that I can pick is 2, 3. And look at that. If this is x, vector x, and this is vector y, what will be the sum? The sum will be 3, 4. The sum will be 3, 4. And so is this 3, 4 in S? To answer that, you just check to see whether A is greater than 0 or equal to 0. And you can see that the 3 is greater than 0. What about Y? Is it greater than 0? Yes. That means this sum is in S. Now, so this second property is satisfied, so I don't need it. I don't need it because the one I need is the one that will show me that, the one that will tell me that it's not a subspace. The first two properties have been satisfied. Let me go for the third property and see what I can satisfy. I want to choose a vector in F. Let me choose 1, 2. Yeah, is it in S? Let me see. 1 is greater than 0, that is okay. And 2 is also greater than 0, that is okay. So this one is in S. Now, we are not told how to choose the scalars. We just told we choose any scalar. So let me choose the scalar that I want to choose is negative 2. Let me get the product of this scalar and x. This time that will be negative 2. And this time that will be negative 4. Now, is this vector, new vector here in S, is it in S? Let me check if it's in S. I'm told that this x, because here my x is now negative 2. But I can see that negative 2 is not greater than 0. What about my y? Is not greater than 0. So that means this one is not in S. So this is the condition that is not satisfied. And that is the condition disqualifying this set from being a subspace. So you look at my working here. That is what I did. I only chose a different vector. So we just choose any vector so long as it fulfills the conditions here. So I've said S consists of those vectors whose entries are non-negative. So we have to use a counterexample to demonstrate that S is not closed under addition or multiplication by scalars. So we will pick any vector in R2 and any negative scalar A. I've chosen a scalar negative scalar. Because if I would have chosen a positive scalar, it would have shown that the product of that is, no, I chose, okay, what have I chosen? I've chosen a negative scalar. If I would have chosen a positive scalar, the product of this positive scalar and the vector would be in X. So I thought, what about negative scalar? What about a negative scalar? So I chose a negative scalar. And that one, the one that told me that this product must be. So I let my vector be 3, 1, and my scalar be negative 7. What about the product of these two? Would be negative 7 times 3, 1, which would give me negative 21, negative 10. Is this new vector in S? I go to the condition that X must be greater than 0. My X is negative 21. It does not meet this condition. And even Y must be greater than 0 or equal to 0. My Y is negative 7, but it does not meet this condition. That means this new vector here is not in S. And therefore, S is not closed under scalar multiplication, meaning that S is not a subspace of R2. So it's very easy showing that a given subset is not a subspace, or even showing that it is a subspace. It's very easy. Let's look at the next example. The next example is this, and it says, let B be equal to R3. Show that W is not a subspace of B, where W is the set comprising of ABC such that the first element is greater than or equal to 0. The first element, we are only given the first element. But nothing is said about the second and the third element. It could be anything. It could be negative, it could be 0, it could be positive. But the most important thing here is that the condition is given to the first element, that it must always be greater than 0 or equal to 0. But nothing, it should be negative. Now look at B here, that W should be a set comprising of ABC, where the length of A square, now if I take A square plus B square plus C square, the result must be less than 1 or equal to 1. So we'll be thinking of what vectors qualify this condition. Let's look at C. W should be a set comprising of elements AB, where B is the square root of n. So that the second element here must be the square root of the first element here. So again, we'll be looking at what vectors contain this condition. But let's go straight to the first one. And we are told that we show that it's not a subspace. That means we think of which one of those three conditions will not be fulfilled, and we just give that one. Which one will not be fulfilled, and that was the one we give. Now, so we've already said that in A here, we've already said that vectors here are of the form ABC, where the first one must be greater than 0 or equal to 0. So we can have vectors like, just give me examples of vectors there. We can have vectors like 1, negative 3, 4. So we are not, there's no problem. We're not concerned with the second and third elements. We are only concerned with the first element. It must be greater than 0 or equal to 0. So this vector therefore qualifies. What about this vector? Does it qualify? This vector? This one does not qualify because the first element here is negative 7. The first must be greater than 0 or equal to 0. So this element, this vector y is not a member of W, but this vector is a member of W. What about this other vector? Z, is it a member of W? Yeah, this is a member of W. I check the first element and I can see it is 0, so it fulfills this condition. So it is Z is in W. So we'll be thinking of this vector, such vectors, and we see want to say, can we have also 0, 0? Can we have 0, 0 in W? Let me call this one vector P. Is this vector P in W? Let me see. Let me check the first element. The first element is 0. Yeah, it fulfills this condition. So this vector is in W. This vector is W. So nothing is said about the second element and the third element. They can be anything. The second element and the third element can be any number. We are only interested with the first element. That means this set has the 0 vector. So I want to check if closure and addition will be satisfied. Supposing I take these two, this one and this, which we say are members of W, X and Y, and then I want to add them. No, X and Z. Suppose I take X and Z and add them. What will I get? I'll get 1. I'll get -2. I'll get 1. If I add this plus that will be 1, this plus that will be -2, 4 plus that will be 1. And I can see the new set formed is in W because the first element here is greater than 0. So that means X plus Z will be in W. That means this set is closed under addition. The closure property under addition is satisfied. But the question is, sure that is not a subspace. So I proceed and check if the other property will be satisfied. I want to check the closure under scalar multiplication. Now, so I've said I pick another element. I pick another vector now. U. I pick 2, 0, 5. This is vector U. And choose a negative scalar. I chose -2. And I want to see the product. If that product will be in W. The product is -4, 0, -10. The question is this vector here in W? The condition for a vector to be in W is this, that the first element must be greater than 0. The first element must be greater than 0 or equal to 0. Let me look at the first element here. It is -4, so that means it does not meet this condition, and therefore this new vector here is not W, and therefore W here is not a subspace of V. And that's what I wrote here. I said that the product beta U is -4, 0, -10, which does not belong to W because the first element, -4, is negative. Therefore, W is not a subspace. Let's come to this. What are some of the vectors here? The vectors whose the sum of their squares, sum of the square of the elements will be 1 or less than 1. Let me see. X. If I have an element like this, a set like this, no, a vector like this, The sum of these elements 1, 0, 0, it will be 1. So this vector here belongs to W. What other one? What other one? We have Y 0, 1, 0. So again, this will be 0 square plus 1 square plus 0 square, and this is 1. So it belongs to W. What about this one? 0, 0, 1. So we have 0 square plus 0 square plus 1 square, which is 1. So it will also belong to W. What about this? What about vector 1, 1, 0? Does it belong to W? Let's just see. 1 square plus 1 square plus 0 square. This will be 2. 2 is not less than or equal to 1. Is not less than or equal to 1. So this vector P does not belong to W. Let's try another one. Let's try another vector Q. A quarter 0, 0. Because we're not given the conditions of the element, what the element should be fractions or whole numbers. Not given that condition. Let's see. What is a quarter square? 0 square. 0 square. Here same as 1 out of 16. 1 out of 16 is less than 1. So this vector is in W. So the question is, for you to show there is not a subspace, think of a vector, because you're using specific examples, and then think of a scalar, then go through the conditions and see whether it's satisfied. What about this vector? What about this vector 0, 0, 0? Is it in W? Let me see. 0 square plus 0 square plus 0 square. This is 0. Well, yes, this 0 is less than or equal to 1. It's less than or equal to 1. So that means this R is also in W. In other words, W contains a 0 vector. W contains a 0 vector. So the question is, show that it's not a subspace. So the question is, which of the 3 properties that we've been looking for is not fulfilled? You've already seen that the first property, that it is non-empty. In other words, contains the 0 vector, has been satisfied. So I want to take X as 1, 0, 0, and take Y as 0, 1, 0, and find the sum. Find the sum. The sum will be 1, 1, 0. Is this sum in W? Let me see. Is the sum in W? Let me see. And 2 is not less than or equal to 1. It's not. So this condition has not been met. Therefore, W does not meet this closure property, meaning that this W is not a subspace. It's not a subspace. That's what I wrote here. I said W consists of vectors whose length does not exceed 1. For instance, W would have vectors like U, V, and so on. But what about the sum of these 2 vectors? It would be 1, 1, 0. But this sum does not belong to W, because if I was to take 1 square plus 1 square plus 0 square, I would get a 2, which is greater than 1. And therefore, that means this part is not satisfied. which means that therefore W is not a subspace. Now let's look at part C. What are the elements, what are the vectors in W? So W will have elements like X, which is 4, 2. Because we are told that the second element here must be the square root of the first element. You can see the second element here is the square root of the first element. W will also consist elements like consist of vectors like 9, 3. So that the second element here is the square root of the first element. Would consist, W will also consist of vectors like 16, 4, and so on. So long as the second element is the square root of the first element. So these are part of the vectors in a W. The fact W will also contain this vector 0, 0. Because the second element here is the square root of the first. So in other words, this W contains the 0 vector. Now, if the sum of any two vectors here in a W is the sum of this, let me take this and this. These two vectors, X and Y, and add, I'll get 13 and I'll get 5. Is this sum in W? In other words, is this B the square root of this A? And you'll discover that 5 is not the square root of 13, and therefore this is not in W. That means this set does not meet the closure property under addition. And this disqualifies it from being a subspace. What about, okay, I will still use, I want to check whether it contains, whether it will fulfill the closure under scalar multiplication of vectors. I was using the vector 4, 2. And let me choose the scalar beta, which is 2. What is beta x? Beta x will be 8, 4. If this product in W is this product in W, that means is this 4 the square root of 8? And you discover that 4 is not the square root of 8, and therefore this product is not in W. So again, this property has not been satisfied, but we only need to show one. One is enough to disqualify this from not being a substance. Just one is enough. So which one did I use in my work? In my working, the one that I used, but see, I used this one. I said W consists of those vectors whose second entry is the square root of the first entry. Therefore, vector U, which has 4, 2, belongs to W. So then I chose a scalar beta and turned the product as 8, 4. And then I discovered that 4 was not the square root of 8, which means that this new vector here does not belong to W. And therefore W is not a subspace. So it's very easy for us to show if subsets are subspaces. Now let's show that now subsets are subspaces, and we start for this we'll be using arbitrary proofs. I like this first example. The first example says, let S be a set comprising of ABC in R3 such that 5A is 7B. Show that S is a subspace of R3. Show that it's a subspace. That means that we do not use specific examples, but we go through the three properties. That one, we show that it's non-empty. In other words, it contains the zero vector. That is, we show that it contains the zero vector. And two, we show that it's closed under addition. And then three, we show that it's closed under scalar multiplication. That's what I've shown here. Let me just take you through the steps. Now, just before I take the steps, somebody else would have written this one. I've said that this is a vector. It's a set comprising of ABC in R3 such that 5 is 7B. So whichever way it's written, you must understand that we're supposed to show that it's a subspace, and therefore we're using a proofs. We are proving it. But let's just first of all show whether it has the zero vector. In other words, it is non-empty. Now, so the condition is this. This is the condition for ABC. You're only given the condition about the first and the second element. The first and the second element. That's the condition again. And if, in fact, when you look at this, it means that if you have A should be the same as 7 out of 5B. That means if I have this, I have no problem with the C. C can be anything. But what I know is that if B is 7, or if B is 5, if B is 5, then this must be 35. This is just an example. I'm just showing you what it means. That A is B times 7 out of 5. That if I have 5 here, times 7 out of 5, this would be, this is supposed to be 7. This is supposed to be 7. That if this is 5, this should be 7. The other example of a vector here would be, like, let me say this is 0. So if this is 10, then A will be 10 times 7 out of 5, which will be 14. So these are examples of vectors here. These are examples of vectors here. But this is not what we want, because we want to show it's a subspace. So we do not need these examples. We do not need these examples. But it's good for you to know what the vectors here will be looking like. And in fact, if I have 0 here and maybe 7 here, then this would be 0. I can also have 0, 0. I can also have 0, 0 as the vectors here. So in fact, that means that S contains the 0 vector. Because if I have 0 times 5, I would get 0 times 7, which would be 0. And therefore, 0, 0, 0 is in S. The 0 vector is in S. Now, I now want to show the closure property, and this is very interesting. And also the other property here will also be very interesting, how I manipulate it. So I let P be a vector, and let me say it's x, y, z, such that I'm using ST to mean such that, using this condition, such that 5 times x would be 7 times y. And also let another vector q, and I call it EFG, be in S, such that 5 of E is the same as 7 of F, using this condition. So I'm letting this be 2 vectors in S. What I want to see is whether the sum of these 2 vectors would be in S. That's what I want to see, whether the sum would be in S. So what will be the sum? What will be the sum of these vectors? P plus Q. The sum would be, just add the corresponding elements, and you can see that I would have x plus e, then I would have y plus f, then I would have z plus g. So this would be the sum. This will be the sum of these 2 vectors. What does this property tell me? This property tells me that I need to show that 5 times the first element here gives me 7 times the second element. That is what I want to show. And if I show that, I'll have shown that the closure property is satisfied. Now, that is very interesting. Let me show that. Let me show that here. 5 times the first element. 5 times the first element. What is the first element? The first element is x plus e. 5 times the first element. I want to show that 5 times the first element is 7 times the second element. So what does this give me? By distributivity, this will be 5x plus 5e. But come here. What does 5x equal to? 5x is 7y. So instead of this 5x, I write 7y. Then there's 5e here. What does 5e become? 5e is 7y. So instead of 5e, I write 7y. So we can factorize, of course. This is 7 into, oh no, what else is this? Was 7f. So 7. So y plus f. So what have I shown? I've shown that 5 times the first element is 7 times the second element. That is what I wanted to show. I wanted to show that P plus Z satisfies the condition given here and therefore is in S. I wanted to show that P plus Q, P plus Q satisfies the condition given here and therefore is in S. And you can follow this working. I will now explain how the working ran through. I've explained how the working ran through. Let me just repeat once more. Using my work here, I've said that let P and Q be members of S, and I want to let P be this and Q be this. And you see, P must be in S. For P to be in S, 5 times the first element must be equal to 7 times the second element. And that's what I wrote here. So that's fine. And also, I want to ensure that Q is in S. For me to ensure that Q is in S, 5 times the first element must be equal to 7 times the second element. And that's what I have here. Now, let me get the sum of P and Q. The sum of P and Q is, I just add the corresponding elements, X plus E. That is my first element. Then the second element would be Y plus F. Then the third element would be Z plus G. Good. After this addition, I want to check whether this P and Q is in S. For me to check if it's in S, I want to check and see whether 5 times this first element would give me 7 times this second element. So I just begin by first times the 5 times the first element. So that is 5 times X plus E. And then use scalar distributivity. So 5 times X plus 5 times E. But I come back here and find what 5x equals to. So instead of this 5x, I write 7y because 5x equals to 7y. And then what about 5e? 5e equals to what? 7f. So instead of 5e, I write 7f. Then just factor out. I'll have y plus f. So what I've shown, therefore, is that 5 times the first element is equals to 7 times the second element. That is what I've shown, and that is the condition here. And this condition has been fulfilled. That 5 times this first element gives 7 times this second element. And what this means, therefore, is that this sum of the two vectors is contained in S. So the second property has been satisfied. Let's go to the third property and see whether it will also be satisfied. So I pick one element, I pick one vector from S, and I want to choose P. I want to pick P, and this P we've been told, I've said that it will be XY, so that 5 times X would be 7 times Y. That is very important because that's the condition given to us. I also want to choose a scalar, beta, in R. Let me get the product of beta P. And when I get the product, I'll get bx, beta x, beta y, beta. Good. Now, what is our role now? Our role is to show that beta P is in S. And how do we show that it's in S? For us to show that beta P is in S, we need just to show that 5 times the first element here equals to 7 times the second element. So let me get first 5 times the first element. 5 times the first element. What does this give me? It gives me beta 5x. There's no problem when you take this other constant outside because of associativity. Associativity of scalar multiplication. This is true. This is true that I can have I can use associativity and commutativity at the same time. Associativity and commutativity at the same time. Now look what I've written here. I've said that 5 times beta x would be beta times 5x. But I know what 5x is. It is 7y. But this is beta multiplied 7y. And of course, this, if I use again associativity and commutativity at the same time, this will be 7 multiplied by beta y. Look what I've shown. I've shown that 5 times the first element here is 7 times the second element. And you can see that. That's what we wanted to show. That this product here is a member of S. That's what it means. That's what it means. So this means that 5 times the first element has given me 7 times the second element. And therefore the product here is a member of S. That's what I did. That's what I did. But let me just again take you slowly by slowly through the working, the typed working that I did. The one that I had written before. And it's the same as what I've just explained, that let P be a member of S and K be a scalar or be a real number. And let P be X, Y, Z, so that the first element times 5 gives me the second element times 7. So what will be the product of KP? So KP, the scalar times this vector, will give me this, which is Kx, Ky, Kz. Now, therefore, what I want to show is that 5 times this first element gives me 7 times this second element. Let me show that. 5, I just pick the first element and multiply by 5. Then you used associativity just before that. Yes, associativity and commutativity. I'll have K 5x. But of course, I know what 5x is. From here, 5x is 7y. So instead of 5x, I write 7y. And again, use commutativity and associativity at the same time. Get 7 multiplied by ky. So you notice that 5 times the first element is 7 times the second element. And therefore, it means the product here is in S. And we've seen that the 3 conditions have all been satisfied. That means that this S is a subspace. It means it's a subspace. So when it's a subspace, we're giving the proof actually. When we are told it's a subspace, to show that it's a subspace, giving the proof. And whenever we are told to show that it's not a subspace, we are coming up with specific examples and then showing that one of the properties will not be satisfied. What is the other example? So I give as many examples as possible to ensure that you are familiar with the concepts before we proceed with the other topic in another video. Now, we are given this set and we are asked to show that it's a subspace. In other words, give a proof to show that the 3 conditions will be satisfied. We are given here a condition for the vectors that will belong to H, that the second element must be negative the first element. So in fact, let me just tell you that we'll be having elements like if y is 3, then this will be negative 3, or this is negative 4, then this will positive or and so on. So these are the kind of elements we are having, that the second element and the first element are equal but different in sign. They're equal but different in sign. That's what this question is telling us. So this vector will be in H, this vector will be in H, and several other vectors that obey this in H. So the question is, show that H is a subspace. So that means, first of all, show that it's non-empty, or show that it contains the zero vector. Of course, 0 is the same as negative 0, which means this set contains the zero vector. It contains the zero vector. Contains the zero vector. Contains the zero vector. Now, I want to show that the additive closure property is satisfied. So I pick any two elements, any two vectors from here, and I'm picking vector u and v. And I want to let u be a b, so that such that b equals negative a. I'm using this condition here, that the second element should be equal to negative the first element. And also I want to pick b, which is mn, such that the second element is negative the first element. Now I want to add these two vectors and see whether the sum, and show that the sum is in H. So the sum of u and v, the sum of u and v will be a plus m. We just add the first elements, then add the second element, b plus m. B plus m. So this is the sum of u and v. Now, my duty now is to show, for me to show that this sum is in H. My duty is to show that the second element is negative the first element. That is my duty now. Let me just show that. Just show that. Let me just take the second element here. The second element is b plus m. And I want to show that this would be equal to negative times the first element. If that is shown, I'll have shown that this sum is in H. Now, what is b plus n? From here, I know that b is negative a. B is negative a. What about n? From here, n is negative m. N is negative m. Now, this right hand side can be, I can put negative outside. I can put negative outside, and when that happens, inside the bracket, I'll have this a plus m. So what have I shown? I've shown that b plus n equals to negative a plus m. In other words, the second element here is negative times the first element. And if that happens, then what it means is that therefore the sum u plus b is in H. It is in H because it obeyed the condition of the vectors that are supposed to be in H. So this vector is in H. That's what I showed here. That's what I showed here. That's what I showed. When you follow this, you understand that's what I showed. I say let U be that, let B be that, such that B is the second element is negative times the first element, and also for this part, the second element is negative times the first element. And so what is the sum? The sum will be this. So can I show that the second element is also a negative times the first element? So I just took the second element. And using this, I wrote B. Instead of B, I write negative n. And instead of n, I write negative m. And then factor negative 1 outside. That is what I have. That the second element is the first element times negative 1. And so, U plus B is in H. Good. Now, this time I want to pick a scalar beta. In my beta, I want to pick a scalar beta from the real numbers. And I want to use my B, my vector B, not my vector B. Actually, this is supposed to be U. Supposed to be beta U. So my U, I had chosen U to be AB. So what is beta U? It will be beta A, beta B. So this is my new vector. I want to show that this new vector belongs to H. How do I show that it belongs to H? I show that it belongs to H by showing that the second element equals to the first element times negative. That's what I want to show. And look at this. This one is such that this one is such that B is negative N. This one. For this one to be a vector in H, B must be equal to negative N. Now, so can I show that beta times B is negative times beta times N? Okay. This is the same as beta, just like that. This is the same as beta. What is B? B is negative. Negative N. I can use associativity and commutativity to write this as beta. So the negative comes out. So I've just shown that beta times B is the same as negative times beta A. So this second element is the first element times negative. So that means, therefore, beta U is in H. That's what I did here. And so the first condition was fulfilled, the second was fulfilled, the third has been fulfilled. Therefore, it means that it's a subspace. H is a subspace. Let's proceed to the next. It's W, no, or it's W a subspace of B, where W is given by this. So the condition here is that the first element plus the third element to give you the second element. So let's go through the condition and see whether they're satisfied. The first condition is to show that this B or R3 has 0, 0, 0. That is the 0 vector. So I know that if I have 0 plus 0, this will be 0. So that means the vector 0, 0, 0 is in R3 or is in B. Because the first and the second element, the sum of that gives me the third element. So already we've shown that W has the 0 vector, so it's not empty. Now we proceed to show that it's closed under addition. And remember the condition here. So we pick two vectors from W, arbitrary vectors, of course. We are not using specific examples. And show that their sum would fulfill this condition. So the second element, the first element plus the third element gives the second element. So let's just pick two arbitrary vectors from W. I want to pick X, vector X, which is PQR, such that the sum of the first element plus the third element gives me the second element. I also want to pick a vector Y, which is EFG, such that the sum of the first element plus the third element gives me the second element. So what I want, of course, is to show that the sum of X and Y is in W. So what is X and plus Y? It will be P plus E, Q plus F, and R plus G. Is this sum X plus Y in W? Is this sum X plus Y in W? So for me to show that X plus Y is in W, I need to show that the sum of the first element and the third element gives me the second element. That's what I need to show. So let me begin with the second element. The second element is Q plus F. Now, using this formula, what is Q? Q is P plus R. Q is P plus R. And what is F? F is E plus G. Now, using commutativity and associativity, we rearrange these elements to get P plus R. So I'm adding the first element of X and the first element of Y. Then the third element of X plus the third element of Y. So what I mean is Q plus F is P plus R plus R plus T. In other words, the second element is the sum of the first element. What is this? This was E. This was P plus E, and then R plus G. Make that correction. This is P plus E. In other words, the second element is the sum of the first element and the third element. In other words, X plus Y has obeyed the condition here. So that means that X plus Y is in W. So you'll go through the workings here again. What I've just been explaining is I've done it here. I now want to show the last condition. I choose a scalar beta. I chose the scalar lambda. I chose the scalar lambda in the real numbers. And then I want to choose vector x, which I already know that is p q r, so that such that the sum of p and r gives you q. That's the condition given here. The sum of the first and the third is the second. Now, so I want to find lambda times x and see whether it will be in W. So lambda times x would be lambda times p q r, which would be lambda p, lambda q, lambda r. Is lambda x in W? Is it in W? So for me to show that, I want to show that the second element here is the sum of the first and the third. So for me to show that, let me check the second element. Dear summers, what is Q? From this formula here, Q is P plus R, which is lambda P plus lambda R. So lambda Q is lambda P plus lambda R. In other words, the second element is the sum of the first element and the third element. What this means is that lambda x is in W. That is what it means. And that proof is clear. You can follow it later. I've already explained what I was doing. Now let's look at the other example. Show that W is a subspace of V. Show that W is a subspace of V. So there is a subspace of V. Again, we're going through the proof. We're not using specific examples. The first thing, let's show that it has 0, 0, 0. So if P is equal to Q and each of them is 0, then you realize that 0 times would have 0 minus 3, 0, would have 0 minus 0, and would have 2, 0, and this would give us 0, 0, 0. And so that means the vector 0, 0, 0 is in W. So that means this W is non-empty. The first condition has been satisfied. Remember here, the only thing you are told that P and Q must be real numbers. That's the only thing you are told. Let's go to the second condition. I want to pick vectors x and y in W. I want to pick those vectors x and y in W. And I want to let x be m minus 3b, m minus b, and 2b. I'm just using this. I'm only changing the elements that I do not use the elements here to avoid confusion. So I just use the other elements. So this I've used A instead of P. I've used B instead of Q. And this is what I have. I also want to choose another vector y, and I call it C minus 3D, C minus D, and then 2D. So that is the other vector that I've chosen. So I want to find the sum of these x and y. I want to find the sum and see whether the sum will be in W. So what will be the sum of x and y? So x plus y. So let's just get the sum. Of course, we are adding the first two, the first elements. So here you can see that I'll be having something like m minus 3b. So the sum will be m minus 3b plus c minus 3d. And this other one will be m minus b plus c minus d. And this other one will be 2d plus 2b. No, 2b plus 2d. Let me just begin with those of x and then followed by those of y that I maintain. Now, so what does this give me? This is just a plus c minus 3 into b plus d. B plus d. And this other one is just a plus c minus b plus d inside brackets. And this other one is just 2 into b plus d. So then what you notice is that this vector here, the new vector, is in the format that we want it. So in this case, my p is just a plus c. My p is a plus c. And my q is just b plus d. So that you notice that what I have here is p minus 3q, and what I have here is p minus q, and what I have here is 2 times q. So this vector is in the format that is needed, and therefore it means the sum of x plus y is in V. That's why I do it, to show that it's closed under addition. But let me show you the working that I had done earlier. So I said, suppose x and y are in W. Let x be that and y be that for some scalars a, b, c, d. So what about the sum? So we have x and y. We've chosen this to be x and this to be y. So the sum will be this. The sum will be this. So this will be this plus that will give me a plus minus 3 plus that. So it's here that I say that then this one becomes my p and this one becomes my q. That my p is a plus c and my q is p plus d. So you can see that this is p minus 3q and this is p minus q and this is 2q. So that this new vector is in W. That means this sum is in W. Now let me show that the scalar multiplication is also also closed under scalar multiplication. That this vector is also closed under scalar multiplication. So I pick a scalar lambda. I pick a scalar lambda and choose a vector x, and I want x to be this. And then lambda is here, and then multiply. So if I multiply, I'll get lambda a minus 3 lambda b, a lambda minus h lambda, and 2. So that means in this case, my p is lambda a, and my q is lambda b. So that I have p minus 3q, and this is p minus q, and this is 2q. That means this product again is in the required format. Let's look at what the required format was. Let me just clear this. Yeah, this was the required format for elements to be vectors to be in W. They were to obey this, and we've seen that that product obeys that. That product obeys that. That's why it's very important. And that means, therefore, since the three properties have been satisfied, it also then means that W is a subspace. Now, there's another way to do that, and I had already talked about it at the beginning, and then I said that I would then come and make it clearer later. And this is the other way to do this problem, is to use the following theorem. The theorem says that let V be a vector space, and let U1, U2 up to UN be vectors in V. Then the span of U1, U2 all the way up to UN is a subspace of V. So this is the theorem, and so it means we can show that this vector here is a subspace by using this theorem. So what we need to know to show therefore is that this vector here can be written as a linear combination of other vectors, which would then mean that those other vectors span R3. And so if that happens, then it then means that this set is a subspace. So the question is, show that this is a subspace. So we think of how can we expand this? How can we expand this so that it's written as a linear combination of other vectors? Now, so I can say that I can expand this as P multiplied, and P goes here once, and here we have 0. So 1, 1, 0. Then plus Q. Q here, 3, negative 3, negative 1, then 2. Negative 3, negative 1, then 2. But I can see that this vector here and this vector here are in R3. These two vectors are in R3. And they have been written as a linear combination of this other vector. So that therefore means that the two vectors here span R3. These vectors span R3. And so if they span R3 and W equals to the span of that, this was W equals the span of that. So it means therefore that this W is a subspace. It's a subspace. And that is one way of doing it. So just expand this and then see whether you can write it as a linear combination of other vectors. And then if you can do that, that means W equals the span of those vectors. And therefore it means that W is a subspace. So that is the other easier way of doing this type of question. Let's look at a very interesting example here. The example says, let A and B be two subspaces of vector space V. Show that the intersection of A and B is also a subspace. Show that it's a subspace. Again, we're just going through the three axioms. So first of all, we want to show that this intersection has contains 0. In other words, the intersection A and B is non-empty. And then also show that the intersection of A and B contains the sum of any two vectors, the sum of any two vectors x and y. Also show that this intersection again, or this intersection, also show that the intersection of A and B contains the product of any scalar times any vector. That's what we want to show. So once we show those three properties, we'll have shown that the intersection is indeed a subspace. And so let's just go through. Now, we've been told that A and B are two subspaces, and that is a very important point to begin with. So if A is a subspace, then what it means that A contains the 0 vector. So 0 vector is in A, because the condition here is that A is a subspace. And the 0 vector is also in B because B is a subspace. And so what this means is that 0 is common to these two sets. 0 is common, 0 vector is common, and therefore 0 is contained in their intersection. Because you know that the intersection of two sets is the set of the elements common to the two sets. The set of elements common to the two sets. So 0, since A is a subspace, it contains 0 vector. It's non-empty, so it contains 0 vector. And since B is also a subspace, it contains 0 vector. So that means 0 vector is in A, 0 vector is in B, and then 0 vector is common to the two sets. So it's in the intersection. So that is what I did here. That's what I did for the first part. Now let's come to the second part. I want to show that the sum is in the intersection. The sum of, so I choose any two vectors x and y. Choose any two vectors x and y in the intersection of A and B. And I want to show that their sum will also be in the intersection. And that's what I want to do. So if x and y are in the intersection, what this means to me is that x and y are in each of these sets. X and y is in A, and also x and y is in B. That's what it means. And remember that A was a subspace. So if A is a subspace, then it means that x plus y is in A. Because A is a subspace, it must contain the sum of any two elements, any two vectors. And also, x plus y is in B because B is a subspace. And what we are seeing, therefore, is that x plus y is common to these two sets. And so what these two mean is that x plus y is in the intersection. X plus y is in the intersection. That's what I did here. So I said, suppose x and y is in the intersection. So then x and y are in A, and x and y are in B. So since x is a subspace, it must contain the sum of these two vectors. And since y is also a subspace, it must contain the sum of these two vectors. And so the sum of these two vectors is called the two sets A and B, and therefore is in the intersection. We've shown the second property. So now I'm left to show the third property. I pick one vector in the intersection. Let me pick x in the intersection. And also pick a scalar. I want to pick a scalar A, the real number A. Now, since x is in the intersection, what this means to me is that x is in A, and also X is in B. So A is a subspace. A is a subspace. So it means if I were to multiply this scalar A by X, the result would be in A because A is a subspace. And also if I was to multiply A times X, the result would still be in B because it's a subspace. So AX is in A, AX is in B, so AX is common to the two sets. That means AX is in the intersection of the two sets. That's what I showed here. AX is the intersection of the two sets. So that therefore means since the intersection of A and B has satisfied the first condition, the second condition, the third condition, it means that the intersection is a subspace. That is the way I can show that. What you need to know, therefore, or if you've not known, you can find out that let A and B be subspaces, of vector space B, vector space B. Show that by use of counter example. We use counter example. Show by counter example that the union that A union B need not be a subspace. Need not be a subspace of B. It's not a must that the union would be a subspace. So we could have other vectors that their union would be subspaces, but we could have others that their union would not be subspaces. That's why I say that you can choose one example and show us that the union would not be a subspace. Now, so the following are the assignments I want you to try. Is the exercise I want you to try with. We've answered similar questions, and just need to go through our examples and see how to do this type of questions. Thank you for watching. We've been looking at how to determine if a given set is a vector space or if a given subset is a subspace. And we looked at the conditions that must be satisfied. We've gone through very many examples. And if you've not subscribed to my channel, remember to subscribe so that whenever I upload a video, you can automatically see it. Thank you for watching.